to give a talk in this wonderful conference. So this is my first time to visiting Switzerland. I really enjoying very beautiful scenery around here. So I really appreciate the organizer for inviting me to this wonderful places. So in this talk, I will tell you about my recent work on the dynamics on one-dimensional quantum many-body dynamics. And we focus on we discuss the Tracy Widom distribution of random matrix theories. This work was done in collaboration with Tomohiro Sasamoto in Japan. And the result I present today is based on these recent preprint papers. So if you have interest in the detail of my results, please check it out. Let me start with a take-home message with these talks. The system we consider today is a one-dimensional quantum spinning model. We especially focus on the better solvable models. They suppose that we have this kind of one-dimensional lattice, and we assume that each side are occupied by up or down spin like this one. Then we would like to study the quantum spin transport, starting from this kind of alternating domain potential state here. Disappear. Disappear maybe. Oh, sorry. Sorry. Okay, sorry. And this alternating domain potential state have upspin occupies every other site in the half of the system, like these ones. After unitary time evolution, these upspin are transported from right to the left region, like this one. And then we focus on the leftmost upspin, which is emphasized by yellow color cell here. This one. This is the leftmost upspin. Then we especially have strong interest in the probability for finding such leftmost upspin at site x and time t. Here we denote the corresponding distribution function of f of x and t. Under this setup, we exactly show that this distribution function f converges to the GUE Tracy Widom distribution of random matrix theory. We obtain this result by using the beta ansatz. In this talk, I will explain how to derive this result by starting from a basic background and motivation. This is the main message of this talk. And here is the outline. The first, I will explain our basic background and motivation. Here, I will explain the recent interest of Tracy Widom distribution in quantum many-body dynamics. After that, I will introduce our theoretical model, namely a folded XXZ model, which is a kind of simpler version of the XXZ model. Using this model, we exactly derive the Tracy Widom distribution by using the beta ansatz. In the third part, I will show how to derive GUE Tracy Widom distribution in the folded XXZ model. And finally, I will show our numerical result, which is beyond the folded XXZ models. This is today's outlines. First, I will go to the background and motivation of this talk. Our background is a glowing surface physics in the one-dimensional classical systems. This is the movie taken from these papers. And when the dimension of the system is 1, the surface height is characterized by the function of h. This is a function of one-dimensional coordinate x and time t. This often many theoretical and experimental research have been done to understand the non-equilibrium fluctuation of the surface height. I think one of the most famous equation of motion is the KPZ equation, which is defined by this one. This equation has 3 terms on the right-hand side. The first term is a simple diffusion term, and the second one is a nonlinear terms. And the last one is white noise. In this sense, this equation is a stochastic nonlinear differential equation. So it looks like that. It is very difficult to solve exactly this KPZ equation, but previous literature succeeded in exactly solving these KPZ equations. And now we know several exact properties of the solution of the KPZ equation. For example, when we focus on the long-term limit, this surface height often decomposes into 2 parts. The first term is initial growth term, which is proportional to time t, and the second part is responsible for the fluctuation. This fluctuation grows in time, and this time dependence is given by t to 1 over 3. And the important point of this fluctuation is the presence of the random variable chi. This random variable chi is strongly related to the random matrix series. In this next slide, I will explain the non-trivial connection between the random matrix theory and the KP's universality class. And here I will especially focus on the simplest initial state, namely flat initial state. This is the initial configuration of the surface height at t equals 0. After time evolution, this surface grows in time. Roughly speaking, the surface height is given by Vt here. And also, there is fluctuation around here. And this fluctuation grows with t to 1 over 3 power exponent. And the chi is the random variables. According to the previous literatures, exact analysis show that this distribution function of chi obeys the GUE Tracy Widom distribution, which is a probability distribution function for the largest eigenvalue of Gaussian orthogonal ensembles. And this Tracy Widom distribution is known to be universal in the sense of the random matrix series. In this way, fluctuation of glowing surface can be characterized by the universal distribution function of random matrix series. Here I will explain the flat initial state. This situation is often called flat class. But we can also consider other initial state. For example, this kind of point-like initial state. If we choose this point-like initial state, the resulting time-evolving configuration of surface height can take this kind of circular configuration. In that case, we can obtain the exact result. And according to the exact analysis, probability function for chi obeys the GUE Tracy Widom distribution, which is the largest probability distribution function for the largest eigenvalue of Gaussian unitary ensemble. This is two famous subclass of the KP's universality class. The important point of this slide is that dynamical fluctuation in glowing surface can be characterized by the universal distribution function of random matrix theory. This kind of viewpoint based on random matrix theory has been originally developed in the context of classical surface growth physics. But recently, this viewpoint have been extended to the quantum many-body situations. This quantum extension was triggered by a very famous paper by Prost and GUE. Here I will briefly explain what they obtained in these papers. In this paper, they studied the dynamics of one-dimensional XXX models. The Hamiltonian is given by this one. This Hamiltonian has XX, YY, and ZZ interaction isotropically. Using this model, this paper numerically studies the spin-spin correlation function in infinite temperature situations. This light figure shows the time evolution of spin-spin correlation functions. The horizontal axis represents spin-spin correlation function, and in this axis, we emerge by the T2 over 3, and the horizontal axis is a rescale site, which is normalized T2 over 3. And yellow and red color show the spin-spin correlation function at different times. And this paper numerically calculates a spin-spin correlation function and finding that this numerical result show good agreement with the KPZ scaling functions. This scaling function is a kind of Prehofer-Spohn scaling functions. Essentially KPZ universality class. Here I don't explain the details. Because of this non-trivial connection between the KPZ universality class and the quantum magnet, many theoretical and experimental researchers have studied the KPZ universality class in quantum magnet. There are many theoretical results, so I can review such a theoretical achievement. But here I want to comment on three experiments. As far as I know, there are three experiments for quantum dynamics and the K-phase universality class. The first experiment was done by a Tenant group in 2021. This experiment used these magnetic materials discussing the dynamical exponent by neutron scattering experiment. And the second experiment was done by a group in Munich. This group utilized outer-core atoms, realizing the one-dimensional XXZ models. Using such an experimental platform, this experiment discussed the quantum spin transport and compare their experimental result with the K-phase universality class. And the last one is the experiment done by Google AI group. This experiment used superconducting qubit. Also, this experiment studies the quantum spin transport in the XXZ models. This experiment also compares their experimental result with the K-phase physics. And here is the comparison between the K-phase universality class and the experimental result. Here I don't explain the detail, but these two experiments compare the spin transport physics with a Tracy Widom distribution like this one. Unfortunately, the experimental result does not show the good agreement with the K-phase physics, but in this way, the Tracy Widom distribution has been explored in quantum many-body dynamics. This is, I think, current status of K-phase universality class in quantum magnet in experiment. So far, I have explained the recent interest of Tracy Widom distribution in quantum many-body dynamics by focusing on the K-phase universality class. But here, I want to emphasize that there is several interesting works for pointing out random matrix theory in quantum many-body dynamics apart from the K-phase universality class. Here I will explain the result reported by these two papers. The first paper is reported by Isla and Lacos in 2013, and the second paper was written by Science, Tracy, and Widom in 2022. The second one is a mathematical papers. These two papers discuss the emergence of Tracy Widom distribution exactly in quantum many-body situation. Now I will explain the finding of these papers. The first, I will explain the setup of these papers. The model they consider is a very simple spin-half XX models. Hamiltonian of which is given by this one. This spin operator is a half spin operators, and we have only XX and YY interactions. You know, this model is equivalent to the free fermion model by using the Jordan-Wigner transformation. In this sense, we can easily diagonalize these Hamiltonians. Using this model, these two papers study the quantum spin transport starting from domain world initial state, where the upspin occupies is half of the system, like this one. This is a setup they consider in these papers. Now, here is a schematic image of the dynamics. This is the initial state. We have a domain world initial state, and after time evolutions, these upspin are transported from right to the left region. Then we can obtain typically this kind of time evolved state. Under this setup, these two papers focus on the probability of finding the leftmost upspin at time t and at site x. In the initial state, this probability function can take very simple configurations because our initial state is a product state. And that's why this probability becomes Kronecker deltas. We have single peak here. But after unitary time evolutions, these upspin, after unitary time evolutions, the quantum many-body state is given by the superposition of many quantum many-body states. As a result, this probability distribution function wider in time. Under this setup, Science and Tracy and Widom exactly show that this configuration can be exactly described by the GUE Tracy Widom distribution. This is a schematic illustration of their findings. Mathematically, this statement is given by this one. So first we define the corresponding probability distribution function by summation of probability p, which the summation can take from x to infinity. Then when we consider the large T limit of this distribution function, Science, Tracy, and Widom exactly show that this quantity converges to F2S. This F2S is defined by this Fredholm determinant with airy kernels. So, this Fredholm determinant representation is nothing but a GUE Tracy Widom distribution. In this way, these two papers exactly find the emergence of a Tracy Widom distribution in the XX quantum many-body dynamics. And here is a numerical check of the Tracy Widom distribution in the XX models. So the left figure shows the time evolution of probability of leftmost upsmith. Horizontal axis represent site labels, and the vertical axis represent probability of leftmost upsmith. And the different colors show the probability at different times. So as I have explained in previous slides, the initial state is a canonical delta. So this T equals 0 data can take like these ones. But after unitary time evolutions, the quantum many-body state is given by the superposition of many-body state. As a result, this distribution function the values of this distribution function are wider and wider in time. Then we obtain these time sequences. Using this numerical result, we normalize horizontal and vertical axis by the power function of t's. For example, we multiply the t to 1 over 3, and the horizontal axis is normalized t to 1 over 3. After this rescalings, these different data can be collapsed to one single universal gauss. And here, this plucked dashed line represents a GUE Tracy Widom distribution. This result clearly shows a good convergence to the Tracy Widom distribution in the XX models. This is a kind of visualized explanation of emergence of Tracy Widom distribution in XX models. But this convergence to the Tracy Widom distribution has mathematically proved by Science, Tracy, and Widom.
Can I ask a question?
Yeah.
So, in this example, I kind of understand what's happening because there's some determinant underlying the phenomenon. Right? So you have some determinant, then it converges to Tracy Widom. In the original KPZ example, is there also some determinant that I can write down that has this connection, that makes this connection Tracy Widom?
The connection between this result and the KPZ equation is unclear to me. As far as I know, there is no direct connection.
Right.
But to my understanding, this determinantal structure comes from the free fermion nature.
Exactly, yeah. Yes, that's clear, yeah. But I mean, I guess to go back a long way. So, you know, we have this KPZ equation and it maps on Tracy Widom somehow.
Yeah, right.
How does that mapping work?
Mapping between KPZ equation and what?
And the Tracy Widom distribution.
Mapping.
I don't know, the emergence of Tracy Widom.
The exact solution, KPZ.
Yeah, but I guess is there a determinantal structure to the exact solution?
If I correctly understand, the exact derivation of the Tracy Widom distribution in the KPZ equation comes from the ASEP. We first consider ASEP. And the ASEP have analyzed by the Tracy and Widom. We have exact, determinant.
I see. Thank you.
Using that exact formula for ASEP, we can go to the KPZ equation under the weekly asymptotic limit or something like that.
Okay, thank you.
Sorry.
that's one way of deriving some determinant formula for the KP's equation. But one can also study KP's equation directly by using what is called replica method. So then one has to do some calculations based on Bayes answers and take some generative function. But in the end, one can arrive at some determinant expression also for the KP's equation. Then if you take the scaling limit, you get a Tracy Widom distribution.
I see. So in some sense, I guess, can I interpret that determinant as some kind of free fermion problem that's equivalent to KPZ?
It's a bit tricky point, right? Yeah, KP's equation is related to delta Bose gas. This is beta and that's solvable, but not really a free fermion.
Right. So it's different.
After doing these replica calculations and take generative function, somehow you get determinant.
Okay, thank you.
I can explain later more.
Thank you for comment.
Sorry, maybe you already mentioned this. So even if I start with alternating sites in the XX case, you get the same thing? Or?
No. If we consider the alternating domain or initial state, this distribution becomes very different.
Even in the XX?
XX. So if we consider dynamics starting from alternating domain or initial state, we have additional factor in front of area canvas. We have 1/2 here.
Okay.
And that distribution is very different from the Tracy Widom distributions. Any other questions so far? If not, I will go to the next. And here I want to emphasize that this result is based on the XX model. So there is no interaction terms in the Hamiltonian itself. Then it is natural to ask what happens when consider the interacting many-body models. This is a very natural question. And there are several numerical work to answer this question. Most of study utilize the numerical method, and previous literature studies the dynamics of spin half XXZ models. Because of the presence of the GZ interaction, we have this model is interacting quantum many-body models. These previous literature have studied the dynamics of XXZ model by using that DMRG, and this paper shows very inconsistent result each others. Some paper shows the disappearance of the GUE Tracy Widom distribution, but other paper argue the appearance of the GUE Tracy Widom distribution. Currently, the emergence of the GUE Tracy Widom distribution has been elusive in the numerical studies. On the other hand, there are one mathematical result, which was reported by Science, Tracy, and Widoms. These three guys tried to exactly solve the one-dimensional XXZ model by using the beta ansatz. But they haven't obtained a clear result on these issues. So from the analytical and numerical perspective of these issues, we haven't obtained any conclusive result on these issues. This is the current status of the Tracy Widom distribution in the XXZ models. So here, let me briefly summarize our backgrounds. The previous literature have exactly derived the Tracy Widom distribution in the XX model. But this XX model doesn't have any interaction Hamiltonians. And several numerical work address this question by using the XXZ model, but it is elusive whether or not Tracy Widom distribution can still emerge or not. From this background, I'd like to pose a very simple question here. So can we exactly derive the GUE Tracy Widom distribution in interacting quantum many-body models? The important point here is that we do not focus on the XXZ models. So I think XXZ model is very difficult to exactly solve. To avoid such difficulties, we focus on the simpler version of the XXZ model. That is the folded XXZ models. Using this folded XXZ model, we can exactly derive the GUE Tracy Widom distributions. In the remaining of this talk, I will explain this result in details. This is our motivation for these talks. So now I will go to our result. So before going to our result, do you have any question or comment on so far? If not, I will go into the detail of my result. Okay, so the model used in the previous work is a one-dimensional spin half XXZ models. The Hamiltonian is given by this one. We have XX and YY interaction. These two terms is identical to the XX models. But this model has a ZZ interaction here. And this delta is responsible for the length of the ZZ interactions. You know this model is a very solvable model, but it is quite difficult to exactly calculate the time-dependent quantities. To avoid such a difficulty, we focus on the large delta here. By using the Schrieffer-Wolff transformation, we can derive the effective model corresponding to XXZ models. The resulting Hamiltonian is often called folded XXZ models, which was originally discussed by maybe this paper. And you can see that this Hamiltonian has simultaneously act foci, J minus 1, J plus 1, and J plus 2. So when we apply the Jordan-Wigner transformation to this folded XX model, we cannot obtain the quadratic fermionic Hamiltonians. In this sense, this model cannot be mapped to the non-interacting fermion only by the Jordan-Wigner transformation. This is the meaning of the presence of the interaction of this model. This model has several good properties. One of the most important property is here. So this model is bed solvable. So we can exactly construct many-body wave function by using the many-body wave functions. And the second important point is scattering amplitude is very simple. This is a scattering amplitude for the folded XXZ models. So K1 and K2 is a wave number of two magnons, and by applying the conventional Bethe-Ansatz method to this folded XXZ model, we can obtain this scattering amplitude. This form is very simple. Because of this simple form of scattering amplitude, we can exactly calculate the probability function for the leftmost upspin. Here I will explain this point in detail. And using this folded XXZ model, we study the dynamics starting from this alternating domain Borel state, where the upspin occupies every other site like this one. And under this setup, we want to calculate the distribution function f, which is the distribution function for the leftmost upspin, and which is defined by summation of p. And here p is the probability of finding the leftmost upspin at site x and time t. Then under this setup, we try to exactly calculate the distribution function f by using the Bethe-Ansatz. This is our theoretical setup. Now I will explain how to calculate this quantity by the Bethe-Ansatz now. So now I will go to our exact result based on Bethe-Ansatz. Before going into the detail, I'd like to first show our main result. So our result is here. So the distribution function in the folded XXZ model converge to the GUE Tracy Widom distribution F2S. This is our main result. And mathematically, this statement is given by this one. We consider largely limit F. This quantity converge to F2S. And this F2S is defined by Fredholm determinant with airy kernel here. As far as I know, this is the first exact derivation of the GUE Tracy Widom distribution in an interacting quantum many-body system, which cannot be mapped to the free fermion only via the Jordan-Wigner transformations. Yeah, this is the main result. And now I will explain how to derive this result. But our derivation is a bit technical, so in this talk I will show the very brief sketch of these derivations. Our derivation can be decomposed into three steps. The first step is to derive the exact integral formula of probability function P. This first step can be done by the Bethe-Ansatz. And the second step is to derive the second step is to compute the distribution function f, which is defined by this one. But after this calculation, we obtain very complicated expression. But we can simplify this expression by using the technique of 6-vertex models. And finally, we take the long-term limit for distribution function. After this long-term limit, we can show that this f converges to the GUE Tracy Widom distribution. So now I will explain this derivation step by step. The first step is to derive the exact integral formula for probability p's. Therefore, for this purpose, we first expand quantum many-body state by this basis. This basis represents the site occupied by upspin. So x1 xn, the site occupied by upspins. Using this basis, we can reduce our problem to the following equations. So the first equation is the equation of motion for the wave functions. And the second one is a boundary condition coming from the constraint. And the last one is the initial state. So this is the equation we have to solve now. Then this equation looks like a bit complicated, but this is a better solvable models. So we can exactly solve this equation of motion. Here I try to apply the beta ansatz. But there's one important key ingredient. So what I use here is a beta ansatz developed in the classical stochastic processes. So this is a bit different from the conventional beta ansatz used in the quantum many-body situations. So here I don't explain the detail of this method, but if you have interest in the detail of this method, I recommend this paper by Schutz or Tracy and Widom. But anyway, we apply this beta ansatz method to our 4-digit XXZ models. After this application of beta ansatz, we obtain this exact expression for many-body wave function in the 4-digit XXZ models. So here we have EXI, which given by GUE over 2 plus 1 over 2 GUE, which correspond to the eigenvalue of the 4-digit XXZ models. And this S is the scattering amplitude, and the capital A is the product of scattering amplitudes. Using these notations, we can construct a many-body exact wave function like this one. This expression a bit complicated because we have summation here, and we also have integral here. But we can show that this is exact. Using this exact many-body wave function, we can directly calculate the probability function P by definitions. And the resulting expression is given by this one. In this notation, we have 2 complex integrals, and we also have 2 additional summation over the nth permutations. This expression looks like very complicated, but this is very convenient to derive the GUE Tracy Widom distribution. The next step is to compute the distribution function f, which is defined by this one. And now we have exact expression for p, like this one. So now I substitute this expression into definition of f. Then our task here is take these summations. This task is very easy, and after this calculation, we can show that this probability distribution function take a similar complicated expression like this one. This expression is very complicated, but we can make this expression very simple by using the 6-vertex model. What I use here is the identity obtained by Cantini, Colomo, and Planck in 2020. This identity was obtained in these papers. The 6-vertex model is related to the XXZ model. So this model have a parameter delta here. This delta corresponds to the GZ interaction in the XXZ models. Then when we take large delta limit, we can obtain other identity corresponding to this one.
Simple question. In the previous slide, what happened? So how did you convert that summation y equal to x to infinity? Where did that go here?
Oh, I see. The point is this, how to say, this is a contour of integrals, and this contour is a circle, but the radius is smaller than 1. And because of such a constraint, this summation can be converged.
Okay, thanks.
The measure of integration has, I mean, the integral has poles when some of the variables of integration differ by some quantity. I mean, it's hard for me to recognize exactly these integrals, but I think that I mean, the measure, the integrand contains some poles, I think.
Yes,
Yeah.
of course. There's a pole.
Yeah.
That's why this doesn't vanish.
Yeah, no, but I mean, if you start moving the contours of integration to separate the integrals, you encounter these poles at the different. I mean, when two of different variables of integration differ by some quantity, these integrals have poles.
Yes, you're right. There is a pole. Yeah.
There might be other poles that make this.
Exactly. Yeah.
Okay. Yeah. Thank you.
Any other question on this slide? No? Then I will go to the next. And this is the identity we use here. And by taking the large delta limit, we can obtain other identity corresponding to this one. Using this identity, we can make this expression become symbols. The resulting expression is this one. So we can derive that this expression becomes a single determinant with kb. And kb is defined by this one. Here Jm is a Bessel function of the first one. In this way, we can derive the very simple determinant or representation of distribution function in 4-digit XZ models. And finally, we take the long-term limit of our distribution function f. For this purpose, I will introduce 3 scaling variables s, y, and z, which is defined by this one. Here I will explain the physical meaning of this choice of the scaling variables. So this is a schematic image of the time evolution of probability function for the leftmost upspin. Horizontal vertical axis is a probability, and the horizontal axis is lattice labels. The initial state is Kronecker deltas, so we have single peak here. But after unitary time evolution, this probability propagates from right to the left like this. And this center of position is proportional to time t, and more precisely, this position is given by 2 minus t. This 2 minus t corresponds to the 2 plus minus t here. And this values of probability grows in time, and this time dependence is given by t to 1/3. This values grows in time with this power laws. Because of this time dependence, we introduce this time dependence function here. This is a physical meaning of the scaling variables. Using this scaling variable, we can easily take the long-term limit. This is our exact expression for the determinant with Bessel function. And using this scaling variable, we can easily take the large C limit, and the resulting expression becomes Fredholm determinant with ARE kernels. Now this is nothing but a GUE Tracy Widom distribution. Now this is a very rough sketch of our derivation of the GUE Tracy Widom distribution in the 4-digit XXZ models. So now I will finish our main result. So now I will go to our numerical study beyond the 4-digit XXZ models. So do you have any questions so far? No? So I will explain our numerical study beyond the folded XXZ models. So what we have obtained so far is exact analysis of folded XXZ model. In that case, we can exactly calculate the probability of leftmost upspin. And but in this case, we focus on the effective model of XXZ model. But what I really want to know is the dynamics of XXZ model itself. But you know, this XXZ model is very difficult to exactly solve. So that's why in this talk I will rely on the numerical simulation based on the tensor network algorithms. And this is the Hamiltonian we use now. This is a XXZ model with open boundary conditions. Using this model, we try to study the emergence of Tracy Widom distribution in the XXZ models. Here is a new detail of our numerical simulations. Our numerical method is a time-evolving block decimation method, which is a kind of tensor network algorithms. And the lattice number we use here is L equal 100. And the initial state is an alternating domain wall state, which is completely same as the initial state of the folded XXZ models. In this case, we have upspin like this one. Using this initial state, we numerically calculate the probability of finding the leftmost upspin outside X and time t. And here is a new definition of the probabilities. We numerically calculate this quantity by tensor network algorithms. And here is our numerical result for the XXZ models. These three panels show the time dependence of probability of XXZ model with different three value of deltas. The first, let's take a look at these light figures. This is a numerical result with delta equal 20s. This corresponds to the large anisotropic inflection case. In these figures, we normalize the horizontal and vertical and horizontal axis by the power law function time t. For example, vertical axis is multiplied by t to 1 over 3. And this p is the probability of leftmost upspin. And the horizontal axis is normalized by t to 1 over 3. And this graph, the numerical data at a different time is denoted by different colors here. And this dashed line represents GUE Tracy Widom distribution. This result clearly show that numerical data show the good agreement with the Tracy Widom distribution in this case. This behavior is very consistent with our exact analysis of folded XXZ model, because folded XXZ model is an effective model of large delta limit. But when we decrease the value of delta here, this is delta equal 10, and this left one is delta equal 5. If we decrease the value of deltas, we can clearly see the large deviation from the GUE Tracy Widom distribution, like this one. Currently, I don't know the fate of the Tracy Widom distribution in the long-time limit, because this is a numerical simulation. The system size is finite, and the time scale is also finite. Because our numerical method is a tensor network algorithm, so we cannot access large long-time scales. So I don't know what happens this distribution becomes. But naively, I expect that Tracy Widom distribution doesn't appear in the long-time limit, in the thermodynamic limit. But this is just guess, and I don't have any conclusive result on this topic. But I'm expected such behaviors.
So can I ask you a question about like the truncations in this tensor network method? So, you know, if I look at the delta equals 5 data, it looks as if it might be kind of noisy. So, I mean, do you have error bars, like, versus truncation error? Like, yeah. What kind of truncation error are you targeting?
I will evaluate that. And this is well converged.
I see.
But times are smaller.
Sorry? Yeah.
Okay, sorry. Can I a general question, not necessarily related to the numerical simulation. So your domain wall, on the extreme left, everything is spin down, which is like empty sites. So if you play around with that in the sense that you have some finite amount of, will that change the Tracy Widom? Or what would you do? Like you can, even for the XX model, you can play around with this.
Yeah, this result is very sensitive with the choice of the initial state. As you said, we use different initial state. This Tracy Widom distribution breakdown, even finite time scale. This is my numerical observation.
I see.
And sorry, he's asking something. Oh, so sorry, I can't follow your questions.
No, I was just remarking that your times are, the value of times are not so large, so that's...
Oh, sorry, yeah.
Also true, yeah.
But it looks like it's getting worse with large time on the left, right? At -6 or something like that. So it looks like it doesn't converge to Tracy Widom.
Doesn't converge.
That would be your intuition, right?
My intuition, yeah, I don't expect Tracy Widom distribution around here. But
I would.
okay. Why?
So can I ask?
Because I would say,
Why would you expect Tracy Widom? What is the intuition behind
I mean, naively, I would say, like, you're moving in vacuum, right?
Yeah.
So you're looking at a front of something expanding into vacuum.
Oh,
you don't expect interactions to do much intuitively. Okay, I mean, it's not a proof, right? But I don't know.
That is what I expect. I expect initially, but our numerical solution doesn't support that observations. I did many numerical simulation concerning this topic, but as far as I did, I'm suspecting the emergence of Tracy Widom distribution in the long time limit. But this is not a proof, and we need some more rigorous discussion on this topic. But currently, we don't have any conclusive conclusion on this topic. Yeah.
But what's the statement for delta equals 0 and these initial conditions? I understood you to say that in that case it's not Tracy Widom.
Which initial state?
Well, the initial state that you're using for these pictures.
Yes, in that case, the Tracy Widom distribution doesn't appear.
Right. So something must happen somewhere between delta equals 0.
I expect so, but I don't know which.
It could happen at delta equals 1, right? Because that's where most things
Yes.
are.
Okay. Yeah. Sure.
It is a very good point, and I'd like to really understand that point. But now I don't have any rigorous argument on this point. This is a kind of numerical analysis.
So the difference in the initial states is that for XXX you take ups and down, and for XXZ delta large you are taking up and antiferromagnetic or NEL or.
You are asking the XXZ model with completely linear initial state?
Yeah.
Sorry. So I did
with NEL versus fully polarized.
So this is XXZ model with completely domain wall state. This is not alternating domain wall state. This is a domain wall state. If we numerically solve the Schrödinger equation with XXZ models, this is a delta equal 0.5, and this is a delta equal 1, and this is a delta equal 1.5. So this figure clearly shows that there are many oscillations around here. So if a Tracy Widom distribution appears, this peak should be single peaks. But we study the dynamics starting from domain wall initial state. We can't find such a single peak in the probability. That's why I don't expect Tracy Widom distribution in the domain wall initial state case. Do I answer your question?
Actually, I don't understand this figure. So where's the domain wall initially located? Is it at site 50?
Oh, the domain wall around here, like this one.
Okay, and we're looking at the rightmost particle or leftmost particle?
Sorry, this is the rightmost particle.
Okay, good.
Sorry. I'm really sorry. This is the initial sorry, this is an inverse constellation for this case. Sorry.
No, this is. Okay. Sorry, this is which model? This is.
Sorry, could you say again?
This is for XXZ.
XXZ.
Not folded.
Not folded. Yes, it's a finite deltas.
Folded, nothing's going to happen with the state, right? Just nice.
Exactly. The domain world state is the eigenstate of the folded XXZ models. That's not dynamics. Okay. And this is our unique result. And currently, I don't have any conclusive result on this topic. In future, I'd like to understand this physics rigorously more. And here is summary of my talks. So in this talk, I first explained the recent background of Tracy Widom distribution in quantum many-vary situations. And in the previous study for free fermion case, we have exact solution of the Tracy Widom distribution. But in the XXZ model, we don't have any exact solution on these topics. Yet to answer the question, what happens when we consider the Tracy Widom distribution in an interacting quantum many-vary model, we use a folded XXZ model, which is a simpler version of XXZ models. Then we can, fortunately, exactly solve the folded XXZ model. We can exactly derive the Tracy Widom distribution. And additionally, we show our numerical simulation for the XXZ model, and we find the deviation from the GUE Tracy Widom distribution. But currently, I don't know the real fate of the Tracy Widom distribution in the thermodynamic limit, and I really understand the Tracy Widom distribution as an XXZ model, but currently I don't have no idea on how to do it. So if you have any good idea, please, I'd like to happy to discuss with you. So this is the end of my talk. Thank you very much.
We have time for questions, yeah?
I don't have a good idea, but
Yeah, you should have a good idea.
but I have a question. I mean, you could forget about the XXZ and just look directly at the six-vertex model. I mean, just, that's a nice model by itself, and the question you're asking is also well posed. I mean, and there are sort of other results on methods on six-vertex model which might be useful. So did you ever sort of investigate that direction?
Talking about real weights or unitary weights?
No, I mean, you're exactly the same. You take the diagonal transfer matrix and then you put, exactly this kind of domain wall initial condition. I think there's sort of a natural translation.
Is it the unitary one? Unitary dynamics? Or?
No,
That's not the real.
not unitary dynamics.
Okay.
Just the transfer matrix evolution.
Statistical mechanics.
So you took very specific initial condition.
Right.
Could you apply your method also to get exact results for other initial conditions?
It depends on the initial state, but
let's say something like you have 1 up, 2 downs, 1 up, 2 downs, stuff like this.
I didn't do that, but I guess in that case, Tracy Widom distribution disappear. I guess.
But I mean, this sounds a bit strange, right? Because you want to study some I don't know, some universal behavior, I guess, right? It's just this particular initial condition, right?
Yeah. Initially, I want to find universal behavior of this model, but I think our result is very sensitive to the initial state, unfortunately. This is what I obtained here.
But in the free fermion case, you see that there is no difference, right, between having a nail or a domain wall.
But there is. I think you don't get Tracy Widom. For free fermions, you don't get Tracy Widom with domain wall, right?
Domain wall case, the free fermion with domain wall initial states show the Tracy Widom distribution.
Right, but with nail you don't get.
Nail doesn't. Yeah, nail state doesn't appear the Tracy Widom distribution.
You get GUE probably.
GUE? No. The free fermion consider the free fermion with alternating domain or initial state, we have additional factor in front of the area kernel. We have 1/2 here. This distribution is very different from the Tracy Widom distribution. That's why we don't have any Tracy Widom distribution in the narrow state in the free fermion case.
I think one conjecture would be that the Tracy Widom seems to show up whenever you have like a fully filled state of magnons in the right half. And so for the free fermion case, that's full filling, and for the folded case, that's half filling. And so maybe for finite delta, you need to create the same quasi-particle content of like sort of the fully filled state of magnons, which might be a slightly different state.
Right, the ground state.
Yeah,
I mean, the nail state is the ground state,
Yeah.
so that's infinity. So
I see.
yeah, and so it could be you have to like go to whatever that ground state is in order to.
Thank you.
Okay, let's